Hello. In this video, I want to show you how to solve this problem. It is 2022 AMC 12A problem 16. So this problem gives us a definition of a triangular number. Is this the sum of the basic arithmetic sequence from 1 up to n? So we know it is equal to n times n plus 1 over 2. It's pretty basic, right? So the problem tells us that for some n's, t sub n is a perfect square. So it lists the first several perfect squares for t sub n's. So t1, t8, and t49. Okay. So it asks us to find out the next perfect square. Okay. So because we need t sub n to be a perfect square, so let's write it in the equational form. Let's say it is equal to k squared. So now our job is to solve this integer equation, right? So let me put 2 to the right-hand side. Then we get this equation. So how to solve it? Of course, a very light way is to try different n's from the smallest. So we already know the third smallest is 49. So maybe you should start from trying 50, right? You keep on increasing the value and see for what n this equation holds. So this is a very bad idea, right? Because we have no idea about how small the next feasible n is, right? So how to use the mathematical way or the strong mathematical reasoning to solve it? So for this equation, this is the key observation. So for the left-hand side, we have the product of two consecutive integers. So the key fact for two consecutive integers is that they are relatively prime. Right? So what is the implication? Well, so let's think about the right-hand side. And for the right-hand side number, let's say we do the prime factorization of the right-hand side. Okay? So after doing the prime factorization, you know that to make equation hold, so we'll have to assign some factors on the right-hand side to the first term on the left-hand side in. And we have to send some other factors or the remaining factors on the right-hand side to the second term on the left-hand side n plus 1. But in this allocation process, we have to make sure that n and n plus 1 cannot have the same prime factors. Otherwise, they will not be relatively prime, right? So this is super important in the following sense. So first, we observe that the right-hand side has 2, right? So these 2 must be sent to either n or n plus 1, right? So think about it. Suppose 2 is sent to n. Then n is even. So it implies that n plus 1 cannot have 2, right? It must be an odd number. And suppose 2 is sent to n plus 1, then it implies that n must be an odd number because n plus 1 is even, right? This is the first observation. The second observation is here. So let's look at k, okay? So say, let's do the prime factorization of k. Suppose somehow we get a prime factor, say for instance, is equal to 7. And its multiplicity is 5, okay? Suppose this is one factor in k. And please note that on the right-hand side, we have k squared. So that means that for k squared, if we do the prime factorization, then every prime factor has the exponent that is even. For example, if for k, 7 has multiplicity 5. So for k squared, 7 has multiplicity 7 to the power of 10. So the exponent is even, right? And next, let's think about it. So for this time number 7, because it needs to be sent out to the left-hand side. So how many 7 can go to n? How many 7 can go to n plus 1? Then we must have the fact that either all 7s go to n or all 7s go to n plus 1. We cannot have part of 7s go to n and part of 7s go to n plus 1. Why? It's because if both n and n plus 1 have 7, then they are not relatively prime. So this is the key observation, right? So it means that for any prime factor on the right-hand side, so either all these identical prime factors enter in or enter in plus 1. Because we know that for any prime factor in k squared, because we take a square, so it must appears with an even number of times. And since all of them must go to either n or n plus 1. So it means that suppose this number goes to, say, some number n. So n has a perfect square factor. So for example, if we put this number 7 to the power of 10 and let it go to n, then we know that n has a perfect square factor that is the square of this number. Or if you put this number 7 to the power of 10 to n plus 1, so we know n plus 1 also has a perfect square factor is this number, right? So this is a very important observation. Okay, so it leads to the following structure of the solution. So suppose for the coefficient 2 here, we send it to n plus 1. So then we know that n should not have 2. N is a number, n plus 1 has coefficient 2. And when we do the factorization of k squared and send different prime factors of k squares to n or n plus 1, we know that so they should form perfect squares, right? So we could denote n as a perfect square u square and n plus 1 as 2 times v square. And please keep in mind that u and v must be relatively prime, right? Or another type of the solution is that the coefficient on the right-hand side 2 is sent to n, right? So n could be written as, say, 2 v square, n plus 1 is equal to u square. And again, u and v must be relatively prime. Okay. So now we can see that this equation has a very, very strong structure, right? So let's solve these two types of equations. Okay. So because we are looking for the smallest n, so let's just try the n's. But this time, because either n or n plus 1 is a perfect square, so we just try the right-hand side, right? And see which will give us the feasible solution. For example, we may begin with trying the first equation. Okay. So let me call it equation 1, the second one equation 2. So for equation 1, let's see for so let's first try u squared and see for what values for u that will make n plus 1 to have the form 2 times another perfect square. Okay, so let's try it. So we see that u is equal to 1. This is pretty good, right? Because n is 1, so n plus 1 is 2, so v is 1. So this is good. What about u is equal to, so u must be up, right? So let's try u is equal to 3. So then n is 9, n plus 1 is 10. No, v is not a perfect square, it's not good. What about u is equal to 5? So n plus 1 is 26. No. And what about 7? Yeah, if u is 7, then n is 49, n plus 1 is 50, is equal to 2 times 25, so it's 5 squared. This is pretty good. And let's try some other use. What about 9? It's not feasible because n plus 1 is 82, right? So it's half 41. It's not a perfect square. It's not good. So 9 is not good. What about 11? So then n is 121. So n plus 1, 122. Is half is 61. It's not good. 13. So n is 169. N plus 1 is 170. Its half is 85. It's not a perfect square. 15. N is 225. N plus 1 is 226. Its half is 113. It's not good. 17. So n is 289. Its half is no. N plus 1 is 290. So its half is 145. It's not good. Yeah. At least after trying out this number, so none of them work. It's a little bit unfortunate. But since we have the second type of the solution, so why don't we try the type 2 solutions? And hopefully we are able to find out some small n's or small u and v's that are feasible. Okay. So for u is 1 is not good because n is 0. So what about u is 3? So n plus 1 is 9, n is 8, is half. It's a perfect square, so it's 2 square. This is good. And then let's try u is 5. So then n plus 1 is 25, n is 24, is half 12, is not a perfect square. U is 7. So 7 squared is 49. So n is 48, is half is 24, is not a perfect square. If u is 9, then n plus 1 is 81. Then n is 80, is half 40, is not a perfect square. For u is 11, n plus 1 is 121, is half is 120. No, n is 120, is half is 60, is not good. For u is 13, n plus 1 is u squared 169, is half, n is 168, is half is 84, is not good. Let's next try u to be equal to 15. So n plus 1 is 225, then n is 224, is half is 112, it's not good. Next, let's try 17. So then n plus 1 is 289, then n is 288. Its half is 144. Wow, it's pretty good. So you find a solution, it's a perfect square. It's 12 squared, right? So now we have identified 4 solutions, right? Wow, that's really good. And let's check those solutions with the first 3 smallest numbers given in the problem, right? So let's see what n's we get. So for the first type of the solutions, then u, let's see, u is 1, then n is 1, u is 7, n is 49. For the second group of the solutions, let's see, for u is 3, then n is 8. For u is 17, then n is 288. So these are 4 smallest n's that make the triangular numbers to be perfect squares. So the first 3 smallest numbers are consistent with those given in the problem, right? So actually this verifies that our approach should be correct. Our answer should be correct. So the 4th smallest n is 288. Okay, sounds good? All right. And let's look at the question that is asked by this problem. It asks us to compute the sum of the digits of the 4th smallest triangular number that's a perfect square. So basically, it's not good to just report to 88. We have to compute its associated triangular number, right? So this is T sub n, or T sub 288. So after doing some algebra, you can see this is equal to this number. And this problem asks us to report the sum of all digits. So let's just sum over all its digits. Then we get 4 plus 1 plus 6 plus 6. That is equal to 18.